All right, one more time. Today's lesson is rational numbers and equivalent fractions. What's our objective, class? Get ready?
Rational numbers and equivalent fractions.
Okay, very good. We're going to talk about closed sets. We'll get to that. We're going to talk about rational numbers, comparing fractions, improper to whole numbers, and mixed numbers. So let's start with this scenario. What does it mean to have a closed set under an arithmetic operation? So we know our whole numbers. If I added them to any number that's also a whole number, would my answer also be a whole number? That's my question. Okay, so let's just pick a few numbers and try it. If I added 0 to 2, would I get a whole number? Yeah. 3 plus 0, would I get a whole number? 0 plus 0?
No.
But yes.
0 is a whole number.
Okay, that's the test. So you just have to test a few. And if you can think of any cases that it's not, then you've disproved it. But I can't think of any that would. Every single number here, if I added it to any number here, it's going to be in this whole number set. Even 10 plus 10, it's 20. Well, that's in this set. So we say, if that's true, we say it's closed under addition. What do we say, class? Get ready?
Closed under addition.
Good. Closed under addition. Let's try subtraction. If I took any number and subtracted it, will I still get a whole number? Okay, let's say 2 minus 2, that's 0. Sure. 3 minus 1, that's there. 1 minus 3. Is that a whole number?
No.
No. Therefore, we say it's not closed under subtraction. What do we say, class? Get ready?
Not closed under subtraction.
Not closed under subtraction. You guys are getting this. Let's try multiplication. If I take any number and multiply it, will I still get a whole number? Let's think. 0 times 0. 1 times 0. 3 times 0. Oh yeah. Can anyone think of a case that it's not going to be in here? Emma?
Multiplying regular numbers.
Which
But it's
you're
a whole
right,
number.
but it has to be positive. Okay, but you're thinking good. All right, so is it closed? Yes or no? Yes, this is. They're all going to be whole numbers, so we say yes, it's closed under multiplication. Okay, multiply. All right, so now let's try division. This is our last test case. Is it closed under division? If I took any number, 2 divided by 1. That's 2. That's in there. What if I did 1 divided by 2? That's 1/2. Is that in there?
No.
No. Therefore, division is not closed. Give me a thumbs up if you understand closed. Okay. All right. So most of us. All right. So the idea is to make sure whatever arithmetic you do, the answer is in that set. If the answer's in that set, it's closed. All right. Let's move on. Question, Jasmine.
Does it have to be whole numbers?
You can do that test with integers. You can do it with counting numbers. So we're going to talk about this case. We have a new case that's not in whole numbers. So it's got a special name. It's called a rational number. What is it called? Get ready?
Rational number.
Rational number. Rational numbers, the root word of rational is ratio. So a ratio, here's your root word. That's how I remember. Oh yeah, what's a rational? Ratio. Oh yeah, ratio is like a fraction. So any number, if I can write it as a fraction, it's a rational number. Can I write the number 9 as a fraction?
Yeah.
It's a fraction now. Could I do this? Is 9 a fraction now?
Yeah.
Yeah, so that's a ratio, so it's rational. So a whole number is always rational. What's not rational? Pi, that's not rational because it goes on and on 2, 4, 1, 4, 1, 5, 9, 2, 6, 5, 3, 5, 8, 9-ish or so. And I can't write it as a fraction. Not an exact fraction. How about the square root of 17? This is going to be like this. It's going to be a bunch of just digits that keep going. So that's irrational. This is irrational. This is rational. Because I can write it as a fraction. So, what do we do with that? We could plot them. I'm going to skip this part, but I could figure out what that is. It's going to be 1 2/3 in the negative. It's going to be here. Negative 1/2, 1/2, 1.5, 2 1/3. They all have a spot on the number line. It just won't be on a perfect tick mark. Okay? All right, let's quiz you to see how well you understand whole numbers, integers, and rational numbers. We're going to state if each number is whole, integer, or rational. So I would say, okay, -3. It's on my number line, so it's an integer for sure. Is it a whole number? No, whole numbers go from 0 and on. Is it a rational number? Let's think about that. Can I write it as a fraction? Give me a nod yes or no if you think it's a rational number. You're right, it is. Because look, it's a ratio now. It has a numerator and a denominator, so I say R rational. Okay, I'm going to call in some helpers. Is 2 a whole number? Bo.
Yes.
Yes. So we put W for whole. Is it an integer? Sophie. Yes, it's an integer. It's on my number line, right? Is it a rational number? Spencer.
Yes.
Yes. I can write it as a fraction. Or 4 halves, right? Do the same number. Okay, 3/4. Is it a whole number? Lauren. No. Is it an integer? Avery. No. You're right. Is it a rational number? Lexi. Yes. Yes. So it's only a rational number. There's our ratio. Okay, I think we have a pretty good roll. You guys okay? Colin or Joseph?
So, pretty much any number that you can turn into a fraction is a rational number.
He says pretty much any number you can turn into a fraction is a rational number. Bingo, word for word, exactly, yes. Yep. Any number, if you can turn it into a fraction, it's rational. Okay, we're going to do something cool. Big fractions are a pain. They are harder to work with, they're harder to add, they're harder to multiply. So we're going to, any fraction, if it can be reduced or simplified, we do it. How do we do it? We find the greatest common factor of the numerator and denominator and divide it out. So I do a quick factor tree. The factors of 12 are 3 and 4, 2 and 6, itself and 1. I look at 18, I do a factor tree for 18. I go 9 and 2, 6 and 3, itself and 1. Now I compare the lists. Which number is common to both lists and is the greatest number? Hannah. 6. She says it's 6. Is there anything better than 6? Nah, that's the largest one that's common to both. So 6 is my GCF. What do I do with the 6? I divide it out of the top and the bottom. 12 divided by 6 is 2. 18 divided by 6 is 3. My reduced fraction is 2/3. Is that cool? You can use your prime, well, we didn't prime factorize. We're going to do that next. But that's, you can find your GCF that way. Okay. We are now going to prime factorize to reduce. Okay. So 72. Let's do a factor tree of 72. A factor tree of 108. All right, I'm going to call on some students to help me do a prime factorization tree for 72. Aubrey.
9 and 8.
9 and 8. The 9's Addison? 3 and 3. 8. Let's go, Annika.
4 and 2.
So good. And already I'm seeing prime. Let's do the 4. We know that's 2 and 2. Okay, so my prime factorization for the numerator is 2, 2, 2, 3, 3. I write it all out. Let's do 108. Hannah. Okay, we'll come back and show the next one. Michelle? It's even. Brooke? Oh, is that right? Layla, sorry.
9
You know what? Not very many people know that. That's pretty good. Is she right?
There's a thing right there.
There's 18. There's your 1 away. Okay, good. Break it down 3 and 3, and then let's come back, Hannah. 4 and 3, and then the 4. 2 and 2. Okay. Prime, 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 prime. Let's write them over here. We got 2, 2, 3, 3, 3. This is the funnest part because it's a karate chop. 2 and 2. I missed it. 2 and 2 becomes 1. If it's the same on top and the same on bottom, it becomes a 1. 2 and 2 becomes a 1. 3 and 3 becomes a 1. 3 and 3 becomes a 1. What am I left with? 2 on top, 3 on the bottom. Look at that. That huge fraction really is 2/3. It's kind of a fun way. Some of you, if you're thinking a little bit deeper, or if maybe this was so easy, let me make you think a little bit deeper. What is 2 times 2 times 3 times 3? So eliminate the 2. There's 4. There's 9. That's 36. What's 2 times 2 times 3 times 3? Oh, that's 36. Did we just find the GCF? 36 is the greatest common factor of both, and we used prime factorization to find that. All right, we are going to. I think most of you remember what an improper fraction is and a mixed number. Give me an example of an improper fraction. Colin. 3 halves. Why is it improper, Colin? What makes it special?
The numerator is bigger than the denominator.
The numerator is bigger than the denominator. Excellent. So that's called improper. What is it called? Get ready?
Improper.
Improper. To turn that into a mixed number, you divide the denominator into the numerator. It goes once. 1 times 2 is 2. You subtract. This remainder becomes your numerator. The divisor becomes your denominator. So it's 1 1/2. There's our mixed number. And that's all I wanted to say about that. I could say 3 halves could be modeled like this. I got 3 halves, so here's 1/2, 2 halves, 3 halves. That's how I would model that with an illustration. Okay. Use Ross. Page 65, ADILN. Use your whiteboards and your markers. And you take stand-up break.